Although drones have been quite the commonplace for some time now, they still continue to amaze and really give glimpses into what the future holds. And imaging plays a critical role in that future, so that's what we're here to talk about today, defining the future of imaging. Hello everyone, and welcome to another Innovation Summit hosted by Edmund Optics. I'm Scott Bass, Senior Director of Global Marketing for Edmund Optics, coming to you from our headquarters in New Jersey in the US. I will be your guide for today's event. We assembled some of the best in the business where we are going to be discussing how you can achieve precision, accuracy, and confidence in your imaging systems. We have a jam-packed agenda, which you can see on the screen right now. We'll start with our keynote, jump into our first interactive demonstration of the day in the lab on telecentricity, take a break, jump into two other lab demonstrations on manipulating wavebands and distortion. Then another break, and upon return, we'll have our final presentation of the day on ruggedization. After that is your chance to dive in deep with the presenters and other attendees during our live interactive networking sessions. We'll explain that later. So let's get started with our keynote presentation, which is all about precision in design for manufacturability. This keynote will be led by two of our experts here at Edmund Optics. First, we have Greg Hollows, Vice President for the Imaging Business Unit, a 20-year imaging veteran and a highly sought-after speaker on numerous topics. Then we have Virginia Figueroa, Operations Manager for our new manufacturing facility in Tucson, Arizona, another 20-year veteran who knows quite a bit about manufacturing advanced imaging assemblies. So Greg and Virginia are coming to us from our new manufacturing facility in Tucson, Arizona, so you may hear some typical manufacturing noises here and there, so we apologize in advance. Now, without further ado, I will turn it over to Greg.
Thank you very much for the nice introduction, Scott. Hello, my name is Greg Hollows, and I'm going to walk you through our keynote presentation for today. We're going to be talking about precision for the entirety of the webinar and the summit today. But what I want to talk to you about is precision as it relates to the imaging lens design and manufacturing. When we try and do precision in any sort of application, we have to start off with making sure all the components together actually meet the needs of the system and have a nice high precision capability and repeatability unit to unit. I'm going to spend some time on that today. We're going to walk through a number of different things to be considering there. And what I want to start off with is just giving you an overview of what we're going to talk about. I'm going to do a background briefly, just the baseline where applications have been going, sensor technology, things like that. We're going to tie together things that are more of a system level spec, spatial frequency response, and MTF modulation transfer, which is really critical to the lens and how that gets into design limitations and what an actual lens can do for you. I'm going to do some relating to that to actual pixel sizes, kind of taking the background information about sensor technology development and connecting all that together into one package. Kind of gives you kind of the theoretical level, the high level, what can be done. And then I'm going to spend a little bit of time, actually, we'll have an interview with the head of one of our manufacturing facilities where she's going to walk us through some of the things you have to consider and the difficulties with doing assembly work to high precision capabilities. Then I'm going to tie it all together at the end to show off how performance changes with different tolerances and systems. I hope you enjoy the time that we go through this. So let's just jump into the background, just a couple of quick slides here to give you that feeling of where things have been at and where they're heading towards in the future. So if we look at about 20 years ago, then resolutions were a bit lower. 0.3 megapixels was kind of the norm. 9 micron pixels, which is large by standards for most of the industry. And that's about a frequency space, which we'll get into the MTF conversation, a bit of 55 line pairs per millimeter. But the critical part here is that it was 0.3 megapixels of resolution, 9 micron pixel sizes on the sensors. Today, we're seeing resolutions available for the general purpose market in excess of 120 megapixels. We're seeing pixel sizes as small as, or even smaller than 1.4 microns. Now, the 120 and the 1.4 aren't necessarily together, but it's giving you that kind of range of things that can be done. This is giving frequency spaces of 350 line pairs or more, or about 7 times what they used to be from just getting the data next to each other and be able to pull that apart and see it. So we've seen this huge change in sensor technology, which is allowing all kinds of applications to be considered and completed. Having good, precise components to go with those sensors is really critical in order to make things go the way you want them to work. So let's keep that as the baseline for a second. And let's kind of move into the things that we look for when we're testing a system and validating that it's going to work. And then considering the limitations with it as well. So something to keep in mind here when we talk about performance of a system and the precision that's going to be available is really understanding what a lens can do. We look at the limitations of what can be done out there, and there's certain things that can be applied to it. But the first thing to keep in mind is not even a perfectly designed, the best designed lens and best manufacturing lens can actually reproduce all the detail of an object. There is going to be a degradation from that initial signal that's coming off of an object that we're looking at, no matter what it is. There's going to be some degradation from that. That's even if we make the perfect thing. And it's nice that there's actually an equation to allow us to calculate what that limitation is. It basically goes around what is the smallest achievable spot size or detail that we can see. And it's related to just a couple of things. There is a constant. There is the wavelength of light that's used in the F number. Those three things tell you what the absolute limitation of any individual lens design is going to be. We can vary a couple of those things. We can vary wavelengths. We're not going to talk about any of that in this presentation today. We're just going to look at what the limitations are related to F number. And it's important to know that as you change the F number or the aperture setting of the lens, things will increase and decrease accordingly. And here's a nice little chart for you to use and potentially pull out later just to see how things will change. So we look at that equation, we say, what's the smallest achievable spot size? And we think about those pixels getting smaller. We want to see those details that are tinier and tinier. The equation tells us we have to go with a lower and lower F number lens. So this chart lets us see as we vary F number up and down, what happens to other things. So as we make the F number go up, we're going to see the diffraction limit and the resolution of the system go down. As we drive it down, the resolution and diffraction limit of the system go up. It gives us that ability to say, as I can lower my F number, what am I going to be able to see and do? So that gives us one variability that we can do in this. And what I want to do is let you see this as a function of what happened with those pixels over time, that background that we gave you. So I want to start off with that 9 micron pixel that was from the then time period, about 20 years ago. And those size pixels still exist today. But you can see here, using a system that's set at F8, if I run it through that equation, I get most of the detail in that 9 micron pixel. Now, what's critical to understand on this chart that I'm showing here is I'm looking at these pixels in this 4x4 array, this grid, basically 16 pixels total. You'll notice that they're not on pixels right next to each other. They're separated. I need that space in between to actually distinguish them apart. So it is an image as one object that's 2 pixels in size. So let's walk through things a little bit here and see what happens as I go to different pixel sizes, what has to happen to my F number, and then how that applies over to how well the system can perform. If I take that 9 micron pixel and drive it all the way down to a 2.2 micron pixel, what I see is I've now divided up that 1 pixel into basically 4x4 pixels. So I had that 16 pixel array before. I've now divided it in half twice, basically going to 4.5 microns per pixel, and then the 2.2 microns per pixel. So I get 4 pixels across. And you can see here, as I go to the F4 size and then the F2 size, I can get back to getting that information on 1 pixel. Now, there's some things to be keeping in mind there. A lot of things to be drawn from this. The F8 information, that spot that's really large, it's over 16 pixels now. So you're not getting all that information if you're running at that sort of F number in the system, but you are able to see more detail of that spot, the shape of it. So that is beneficial. If I want to see higher levels of detail, higher levels of information, taking advantage to all those pixels, I need to go down to in this case, I want to get really high contrast where I'm able to see that white space in between. I have to go down to an F number of F2. Now, here's the thing to take away. We're not going to dwell on this for very long today, but it's understanding as you continue to make your F number lower and lower, the ability to do optical design to reproduce the information to that theoretical limit gets harder and harder. So there is degradation in the system, and all the things about precision of the manufacturing of the optics, the metal, the assembly of it has more impact on how much the performance will degrade from that perfect lens. So we got to keep all that in the back of our mind. That's what we're going to drive to over the course of the rest of the presentation here. So we can see what happens there. So now when we get into actually what we see in a curve, I wanted to add a couple more pieces of information here. I'm going to look at the 2 F4 spots in the middle. Now, the blue box there shows the information on the right-hand side of this frame. It's showing those 2 objects. Now, they're covering 4 pixels each, but they're far enough apart and they might be blurry that I can actually still see white space in between them. That gives us a nice separation. It gives us lots of information to see and a high level of contrast. As they move closer and closer together, you can see here, I've now put them on 1 pixel on, 1 pixel off, 1 pixel on for the center of that spot. The amount of overlap and bleed of that information coming together will actually pull the trough up and our contrast is lowering. That doesn't mean that we can't necessarily not see detail there. It's just at a low contrast versus the one on the bottom with the F2, where I have high contrast theoretically. So there's a lot of things that come into play with this sort of thought processy, but we have to be considering all these things when we're picking lenses using for different applications. We'll see that in other portions of the presentations today that talk about a bit of that and how detail and contrast is affected in getting precise measurements. What I want to delve into as we move forward here is in the design and manufacturing process, how do I maximize what I get out of the system? How do I get the highest level of precision in the system for both of these examples? The more contrast you have, the better the performance is going to be. The way we do this, and this is another takeaway for you, is this is a curve on the right. This is an MTF curve. This shows a representation of that information as those two objects are getting closer and closer together, as they start bleeding over one another, and that space in between, we're getting down to that 1 pixel. How does my contrast fall off? These sorts of curves like this, they give you that absolute perfect information is represented in this curve. Here's the black line. That's the theoretical limit, the best we can do with that design at that F number. That's integrating all the different sizes of information of that equation of the 2.44 times the wavelength of light times the F number for all the different spatial frequencies we could consider, basically how close and how far apart things are becoming. The other lines are on here is actually what the lens design itself can do to the best of its ability. Very rarely do they get all the way to the theoretical limitations, but this is the best performance, assuming there's no reduction in the precision of the manufacturing of that design. We don't have shifts in elements. We don't have any tolerancing issues. And this is saying how the best performance could be at different areas of the image that's going to be created. Basically the center, near the edge on horizontal, and then at the corners, how well my performance is going to work out, how much is that contrast is going to be there by the lens design. What I want to focus on for the rest of our time here in this first presentation is looking at how tolerancing or lack of precision in the manufacturing will continue to degrade that information. So let's dive into that and see if we can understand that. The key thing to take away too is when we're talking about the lens design part, we also want to talk about FRF, which is more of a system level spec. It's kind of how everything's performing together. It's precision in the alignment of the sensor to the optics. It's in other parts of the system as well as the optics. We're going to delve into just looking at how it affects things on the MTF, the modulation transfer function, which is what the optics do to relay contrast off that perfect object, let's assume it's perfect, onto the sensor. And we're not going to look at SFR very much. We're just going to look at MTF through the rest of the presentation. So let's talk about the manufacturing tolerances in MTF. So I'm going to look at a very simple system here. What I'm going to show you is I'm going to show you the different stack up of errors that can occur. And you're going to start seeing, well, if things aren't in the right spots, I can start having problems. We have a couple of elements here. There's a green element, which is a singlet lens. We have a yellow piece that's in there. It's a spacer between two lens elements. And then we have what's called a doublet. It's two pieces of glass that are basically adhered together. And those are the blue and red elements. Around the outside, I have the white part it's the barrel that holds this all together. And what I want to do is show you how perturbing different things makes the entire system move. So the first example I have here is that the barrel itself is not made correctly. It's got a little too much diameter to it. It's pushing, it's coming in on the element. You'll see the top and the bottom come together, which makes the element push out farther from its ideal position. This is changing the seating position of that first element. Let's assume everything else is made perfectly. You'll see that the first element's in the wrong spot, the spacer ends up in the wrong spot, and both of the next pieces of glass elements are all in the wrong spot. So that's one piece of the puzzle. Let's look at another thing that could go wrong. We could have everything else made correctly, but the first element's thickness, the distance between the front and the back, are not correct. It's thicker in this case. So the first element is in the right spot. So the rays come into the lens and they strike that lens in the right spot. But now it's going through more glass, which creates some problems. And then we have everything spaced incorrectly throughout the system. This creates more problems through the system. Another example here would be the first element's correct, the barrel's correct, but we have a spacer that's incorrectly made to the wrong thickness. So what I'm getting is I have my first element in the right spot and my second group is pushed out of place. That's a problem. I'm changing the spacing. It's going to degrade the system. The next one here is I have a change in thickness of the blue element. It's moving the red element closer to the front surface of the blue element and thus closer to the green element and the spacer. it's going to create some change in the system. Or I could just have the last element having the wrong thickness to it. Now, I wish that it was only one thing in the system that we were trying to correct for. At any given time, you're going to see all of these things together. You're going to have some variation. That's why there's tolerancing on any print that's made. The interesting part about imaging systems is they're designed in a lot of cases to inspect other parts for their tolerances. Yet there are tolerances on these components as well, which stack up into a potential performance degradation, depending on what they are. That's going to hurt or affect the system. Going through the design process, we try to mitigate these things, but they can all stack up to create other issues. Let's take it out one step further. We just looked at things that were moving in one direction. And the reality of the system is we're going to have things that are going to be in the second image here. You'll see the blue and the red element are tilted, wedge or tilt like this. Or you might have things that are decentered. They're not going in position like this very correctly or accurately. And that can create problems as well. When we think of the stack up of all the errors that we have to consider in the average imaging system, we could have up to 500 different things that are in the wrong position and wrong places. This can create all kinds of issues when you're trying to design and manufacture the parts. Just tightening tolerances isn't always the answer. What I want to do is spend a little bit of time discussing with you an interview that I've done with the head of our manufacturing facility in Tucson, Arizona. Virginia is going to walk us through some of the things that go on there, and I hope that this is informative to you about what to consider in your imaging system. We're here with Virginia Figueroa. Virginia is our operations manager, our Tucson manufacturing facility. Nice to have you here, Virginia.
Thank you for having me.
So we've been talking quite a bit about precision in the manufacturing of optics and how precision in general is important for machine vision imaging applications. We wanted to talk a little bit about how the precision in assembly and the manufacturing of the components goes together to create an imaging system. It seems like it could be very straightforward, but is it always straightforward to assemble an imaging lens?
Well, assembling an assembly lens is putting pieces together, components together. And sometimes it sounds simple, but it's not. We have to create procedures. We have to follow different steps to accomplish the goal of putting these assemblies together. So it sounds general, but it's not simple.
It's not simple. So, it's something that must go into that a bit too, is that applications continue to get more difficult, more demanding, and the precision of the assembly has to go up. Is that something you're seeing, and does it affect everything from design to manufacturing of the materials to the assembly process?
Yes, we see that often, especially with our customers. They want high precision assemblies. They want to make sure that their product is going to meet their specification and requirements. So that it does affect the design, the manufacturability, and the output of the components. So the demand is higher nowadays, and it's important that we can accomplish those requirements for these customers. So it's a little challenge, but it's possible. And with the right skills, it can be accomplished.
Great. So the natural thing would be to just get that higher end assembly work done, just tighten all the tolerances, just make everything less variable from the nominal. Is that a straightforward thing to do, or is that actually add a lot of complication, just tightening everything up?
Tightening everything up, that will be expensive because that means that your optics have to be really made to certain high tolerance, same with the mechanical components, and that increases your price. You don't want that. What you want is to have a high precision aligned system and make sure that it meets the requirements that the customer is looking for, but at a lower price, and then make it easier to put it together. And to put it together, it will require, different systems and equipment and applications. But more than anything, it will require certain skills on the employees to meet those goals.
So you mentioned, I heard the word in there, alignment. What do you mean by that? Because it sounds like that you would just tighten everything up and it still lands where it lands. What do you mean by aligning a system?
Well, aligning a system can be different ways. Sometimes you only need to align an optic element in a cell by doing it mechanically, or you can do it optically. Either way, And then you start dropping your cells in the barrel. And one of those components can be considered the key element that is going to be the compensator and help to improve the performance of the assembly. Other way is active alignment, where you doing the alignment of each component or key components in front of a system like an interferometer or an MTF system. So that way it helps you to improve the performance of the assembly and meet the goals of the final requirements.
Great. So it sounds like there's a couple of ways to get that performance up and the assembly capability up. And it isn't just making everything to higher precision per se. It's about aligning the precision and trying to draw it back out after the fact. That's great.
That's correct. Yeah.
Awesome.
It's a system. It's a process that if it's written correctly, step by step, you can accomplish any type of alignment to any assembly or system that the customer is looking for.
That's great. Well, thank you for spending some time with us and explaining some of those things about how to get to the higher precision levels without just making everything more expensive. I know that makes the customer base pretty happy.
Definitely it does. And thank you for having me here.
Have a great day.
You too.
Welcome back. Hope you enjoyed that time that we spent with Virginia, where she was talking about generally the issues that come up in assemblies, as well as what can occur in having to do active alignment to get the compensation of the system up, things that we can do to make things better than just tightening tolerances, increasing costs. Just tightening tolerances is a wonderful idea in systems. It does help. Like I said, the prices will go up. And in some cases, it can actually make the assembly harder as tolerances get closer and closer together. It can be very difficult to put things together if you have no room to let things move as they're going into barrels or being seated together. So it's something else to keep in mind. What I want to start off this next section with, though, is just looking at what happens when we perturb tolerances in a real system. We want to see the degradation in performance and really try to understand that. What we're going to have here is a real design, and we're going to perturb different parts of the system. We're going to see how the performance gets affected on an MTF curve and see how that precision drops. In the example here, the left-hand image shows you the perfect system in the design software. And the right-hand side, we showed you which element we moved. Now, in the designs, what we're doing is we're moving everything 10 microns. For these images, we move them significantly so you can actually see which part is actually out of position to make it easier to visualize. So in this first one here, we move just one element. We're going to find it has very little effect on the system. When we look at the MTF curves, these curves look very, very similar. They look almost identical. So really let you know that if just one thing's off and everything else is perfect, you're probably going to be okay. You probably will see very little difference in the system. That's not the case in every system, but most of them, that's the way it's going to function. Remember, as I talked about earlier, there's like 500 different things that can be perturbed in the system. It's decenter, spacing, wedge, tip tilt, the glass types, things like that. Changes in the glass material will affect these things as well. We have to take all those things into account to understand how much a system is going to degrade. Let's look at what happens here if we actually move entire sections of the system. We move the entire front end 10 microns from the entire back end of the system. Again, not to scale here in the right-hand image, but we want to see what happens on the MTF curve with this. In this case here, you have the whole front set and the whole back set are misaligned. And you'll see from the nominal design on the left-hand side of your screen to the actual what comes out the other end on the right-hand side from just that one tolerance being off, a huge change in the performance of the system. The red line alone, which shows you the performance in the corner, has been dropped by almost half. It really tells you that you can see a lot of performance change by tolerances or precision being off. Let's take another one here. We're going to move two elements. We're going to decenter two of them in the system, the same one that we had before, that third element, and we're going to do one in the back. Again, exaggerated in this image, and let's see how that affects the performance of the system. And you'll see an even more noticeable MTF drop than what we saw before. Let's think back to what Virginia was talking about doing active alignment and compensation. Just tightening the tolerances might help things along, but it's a significant amount in this scenario to get that done. Being able to go back in afterwards and you've designed the metal in the system, you've designed the glass, you've designed the capability to move the components around goes a tremendously long way in allowing us to bring the performance back up. It might be a subtle change that has to be done, but it does allow us to make those changes and get the performance back to where we want it to be, as opposed to just maybe doing the design to desensitize from these problems. That's one of the things that can be done if we're not going to have that compensation in the system, is to design it so it's less sensitive to these things. But what you end up is with an overall lower design performance in general. So in order to get those high levels of design, in some cases, we may have to compensate the system to make it go. At the end of the day, we really want to be thinking of just lots of things that can be done in systems to leverage things. First off, we want to start with the laws of physics. What's the absolute limitation of what can be done? Using some bigger pixels in many cases, it gives us some more room to be forgiving. The smaller the pixels get, the finer the detail, the more these effects can be seen. We want to get away from that. Manufacturing tolerances that we talked about play a huge and key role in getting the precision of the system up to where we want it to be. And we want to take all that into consideration when we're doing things. We want to guarantee that highest level of performance. We might have to make a more sophisticated setup in assembly to make that go and hit the precision. We want to keep all those things in mind when choosing products in order to get good, precise measurements done, regardless of the application. I hope you've really enjoyed the information we've provided here. I'm going to hand it back over to Scott right now, where he's going to introduce the rest of the material that we're going to be covering today. Have a wonderful day.